Good morning. This is a at home or in the office recording of my talk that I gave a few weeks ago. I'm not sure if it gets published, so I figured I might as well just record it. And so it's about the attribute graph. And I want to start off by saying I don't know how this works, but I think we can make some educated guesses based on the information that's out there and based on the dumps you can get. And in my head, it kind of makes sense. And it really helps, I think, to understand how SwiftUI rendering works and how SwiftUI can be as efficient as it is. So let's start building up some code and look at the graph. So here we have a simple counter struct with a body, which looks like this in the attribute graph. And then we can add a button. And so that gets added to the graph. And we can add a handler and a state property. So we can see now that the state property points to the body node, which I think is kind of interesting. So the counter node, um, sort of whenever it's invalidated, it recreates the body node. And whenever the body is invalidated, it recreates the button, or actually not recreates, but more re-evaluates. And likewise, when the state node is invalidated, it triggers a redraw of the body. So it recomputes the body node. And even though in the code, the state is a property of the counter, in the attribute graph, the state actually points to the counter's body, and only if the body accesses that state property. And so the attribute graph really tracks dependencies. It's not a one-to-one representation of what we write in our code, because there the state would be a child of the counter, but it's really saying if the counter changes, the body needs to be reevaluated, or if the state changes, the body needs to be recomputed. And so we can add a content view node with a body, and then we have two separate subgraphs. And of course, we can make the counter part of our content view's body. And so now the graph looks like this. And so if we were to invalidate the state property, for example, that would mark it as pending or as potentially needing recomputation. The body would be marked as pending in the button. And so everything down below in the graph. Now we can actually add a text node to our content view and an h tag around it, and then the graph looks like this. And again, if we were to invalidate the state property, the body would get recomputed, and the button would get recomputed, but the content view will not. What's interesting though is if we look at a preview of this, the moment we interact with that sample, we can see the text jumping, and it gets clearer when we switch from 9 to 10. So the text hello world jumped ever so slightly to the right. And so apparently this graph is not the whole story, because if we look at it, changing the state should not render the content view again, right? And yet the h tag is re-rendering itself and repositioning its children. So what's going on? We can make this step even more clear by adding a frame. And so if the view is a multiple, or the value is a multiple of 2, so in other words, if it's an even number, the frame is going to be 100 wide, otherwise 50. And so we can really see this layout effect in action. So clearly the h tag is laying out again, and yet in the graph we're not taking that into account. And so let's add a print statement as well to the content view body. And we can see now if we tap it, nothing happens, right? So it doesn't get printed. And so it's clear that the content view's body does not get reevaluated. If we print the counter body, we can see every time we tap, we can see a log message appended. Let's hide the preview and actually build up the graph here. I quickly removed the frame modifier again so that the graph is a little simpler. And the first thing to know is that for each leaf node and for some of the layout nodes, there's something called a layout computer. And this is a type and that's in the graph, and other layout computers can ask it for, hey, what's your size for the given proposal, and all of those things. The text has a layout computer as well, and the h tag also has a layout computer. And then the layout computer of the h tag is actually dependent on both the button and the text. So it's dependent on the button and it's dependent on the text. And now it makes a little bit more sense how this could work, right? Like, so if we were to invalidate the state node, for example, that would mean the state is invalid, the body, the button layout computer, and that triggers a redraw or it marks the layout computer of the HTAG as invalid. And then whenever that value is requested, it actually recomputes everything as needed. Now, this is not the entire story. Out of the layout computer, we get two geometries. And again, this is a simplified version of what the attribute graph really does under the hood, but you can think of this as the frame for that button and the frame for that text. So that would be the position and the size. And so that means that the layout computer might be rerunning, but if the geometries never changed, then everything down below in that graph will also never invalidate. And then out of those geometries, we get a display list. And so the display list is for the button, depends on the button's geometry and on the button itself, right? If the title changes or anything like that, we need to recreate the display list. And the display list is a description of what needs to be rendered on screen. So think of this as a drawing command. The text also has a display list. It also depends on both the geometry as well as the text. And then those are combined into the root display list, which depends on both. And it's actually kind of funny how the display list, if you look into it and look a bit inside the framework, it's actually implemented as a preference in SwiftUI. And so in my mind, preferences sort of take multiple values and combine them into one, right? And so in the graph, that sort of means a node with a bunch of incoming edges. That's the combining part. Now, when I give this talk, somebody sent me a message about taking a picture of my of me, and so I asked to send it over. And this is actually what I feel like talking about those things, right? But yes. In any case, let's look at our preview again, because there's more at work here. So what's really interesting is if we clear the console here and then actually switch to dark mode, there's no print statements in the console. You can test this out yourself by running the code yourself, and you'll see that no code gets executed here. And yet the view is re-rendering itself completely, right? The background is re-rendered, the text is re-rendered, the button has a different color. And so how can it happen? Because what parts, like how does it not re-evaluate the graph on the right? So we switch back to light mode, we can still see no print statements. And so again, what we're seeing here in the graph is not the full story. So it turns out that the text is just a description of what needs to be rendered, right? Like it's just saying, for example, hello world. And in order to actually render this on screen, we need to get a font, we need to get a font size, a color, and so on. And so out of the text, we get a resolved text. That's the new node there. And this resolved text depends on the text. If the text changes, we also need to recompute the resolved text. And that's actually the value that's used for the layout computer, right? Not the text itself. Likewise, that currently the text has an error going out to the display list. And of course, that should be from the resolved text to the display list. And the way to resolve this is through the environment. And so the resolved text actually depends on the root environment. And this environment gets threaded through the program. And as the attribute graph builds up, things that read from the environment will actually be able to create a dependency. And so that's what's happening with the resolved text. So anytime for example, the root environment changes and the color scheme changes, that means that that node gets invalid. The resolved text, the layout computer, the HTAG layout computer, the geometries, the display lists, and finally the root display list. And if nothing changes, for example, in the button display list, it won't be recomputed. And then the thing that happens is this will all be marked as invalid indefinitely until somebody requests the root display list. And that will actually trigger a redraw of or a recompute of all the nodes that have been marked as dirty or potentially dirty. So how does that work with modifying the environment? And let's actually remove our counter node here and simplify our H tag to have just two texts. And let's update the graph for this. So the H tag now has two text nodes. They both have a resolved text and they both depend on the root environment. Now, if we add a large title font, that actually modifies the environment. And we can now see that this environment writing modifier is actually dependent on the root environment, and the resolved texts are not dependent on the root environment anymore. So they now observe this modified environment. And that, again, happens as the graph is built up. I guess it looks a little bit more like this in practice. I'm not 100% sure. But what's happening here is that if, let's say, the root environment changes, that will cause a change to the environment writing modifier, which might actually recompute the body. I'm not sure, but definitely like the two texts will change and the resolved texts will change, and the display list down below. And so the attribute graph, as we've seen here, is actually mostly a static thing. It gets, for the most part, built completely statically during initialization of our views. Some parts are dynamic, like if nodes and for each, but most of it is static, and it's all about invalidating stuff, and then the system will request new values, for example, for the display list. The talk here, like there's so much more to say, right? But we're both getting started to the limits of the time and the limits of my knowledge. What I found really helpful to understand the basics of this and a lot more advanced stuff as well is this post by Renz about entangling the attribute graph. It's the first post that I read that actually helped me make sense of this. And I think one of the first posts describing how any of this stuff works. So it's really helpful to understand stuff. As far as I know and heard of, the attribute graph is based on this paper about eval vite, and it's a C++ paper, and 80% of that paper is about C++, but the attribute graphs algorithm is described here. And I'm sure like by now the algorithm has evolved from the paper, but a lot of this behavior you see makes a lot of sense when you understand the algorithm described in this paper. If you want to look at the attribute graph yourself, you can use AGDebugKit. It's the easiest way to get printouts of the dot or the graph structure. Be warned, because the attribute graph gets really complex very quickly, even for simple examples. So don't be intimidated if you see a massive dot diagram there or graphis diagram. On SwiftTalk, we tried to implement the algorithm from the paper, and it seems to be what we would expect. And so if you're interested in that, you can have a look at that. And that's really all I have to say. You can find me on Mastodon or Blue Sky. And if you want to know more about the layout system and how that works in SwiftUI, then check out the SwiftUI field guide. That's it from me.